Good morning, back from the Martin Luther King holiday weekend. First day back at work. About to get to it. I think today is going to be ratios and proportions. This is kind of more of a geometry type of thing, so we're going to get to that. So we first have to have a working definition of what a ratio is. Simply put, the simplest way that I can explain it or give you a definition for it is a ratio gives the relationship between two amounts, all right, between two amounts. So that relationship will let you know that how many times one amount is contained within another amount. That's pretty much the way I see it, or that's a good way to think about it. So it's a relationship between two amounts where it can kind of tell you how much one is contained in the other. So believe it or not, we're looking at a ratio right now. Two amounts. 1 out of 2. 1 out of 4. 1 out of 10. 1 out of 12. 1 out of 6. 1 out of 8. So I have all these different types of fractions. And so let me drive home what I mean by ratios, all right? So this 1/2 has a certain length. That's how long 1/2 is. If I sit it right on top of this, notice how 1/4 and 1/4, which is 2/4, is still equivalent to 1/2. All right, 2/4 is equivalent to 1/2. Let's look at that. 1, 2, 3, 4, 5. 5/10 is the same thing as 1/2. Let's look at this. Look at that. 1, 2, 3, 4, 5, 6 out of 12. 6/12 is the same thing as 1/2. Right here, we have 1, 2, 3 out of 6. 3/6 is equivalent to 1/2. And 1, 2, 3, 4/8 is equivalent to 1/2. So all of these ratios are equivalent to each other. So everything that I kind of demonstrated right here, I'm writing it out in number form right here on the board. Basically what we just found out is that 1/2 is equivalent to 2 out of 4, which is the same as 5 out of 10. That's the same as 6 out of 12, same as 3 out of 6, same as 4 out of 8. All right, 4 out of 8. So the way this works, or the way we verify ratios to see if they're even equivalent, is a simple process. All you have to do is know how to multiply. So you can grab any two fractions. It doesn't matter. This is how you run the comparison. We're going to take that one and multiply it. So 6 times 6 is 36. We're going to take this 12, multiply it this way, right? 12 times 3 is 36. Notice, 36 is still equivalent to 36. If you get a true statement, right? In other words, if both of these are going to be equal to each other when you're done multiplying, you're looking at equivalent fractions. And this is how we do proportions. All right, so that's how similarity works, and that's how we verify. We cross multiply. You might hear the word called cross multiply when you kind of diagonally multiply across an equal sign. If those results are equal to each other, you're looking at ratios that are equivalent. Now, the way that we do this in geometry, the idea is the same, but the way that we present it is going to be different. All right, so that's the only difference, is the presentation. All right, right here I have two triangles. This triangle is called ABC, and this triangle is called DEF. All right, now I also gave you some lengths, like that side length is 3, this one is 6. Come over here, I have a side length of 5, this one is 10. Now this right here is probably going to be the most important thing, because what this does is this allows you to do things with or without the picture. All right. And the way that you want to read this is literally the way that these letters are set up is going to be more important than the way that the picture looks. All right. All right. So what I mean by that is if I go from A to B, which is letting me know I have a side length AB, I'm talking about this side here. See, it says AB, and then I go A to B. So I'm talking about this side here. It will be similar to DE. So if I come over here, there goes D and there goes E. See what I'm saying? So like the way that you read this and the order that you read it in has everything to do with the way that you set these similarities equal to each other when we look at them side by side. All right. So if I go from A to B, then over here I go from D to E. If I say, okay, BC, which is from middle to the end. And over here, I go from the middle to the end, EF. Now, if I go C and circle back around to A, then over here, I start at F and circle back around to D. So you got to keep everything consistent when you start saying things are equal to each other, because what we're going to look at is the way they like to turn these pictures around to throw you off. All right, so if I'm just looking at this triangle first, and I say, okay, over here I have a 3, right here I have a 6, so I'm going to set up a ratio 3 out of 6 or 3 to 6. But then I come around here and do the same thing. I have a 5 and I have a 10, so I set up my other ratio of 5 to 10, all right? So now I have 2 ratios sitting right here. All we have to do is verify them. So look at that, 10 times 3 is 30, 6 times 5 is 30. That means these are similar. And similar shapes are basically the same shape, but they might be 2 different sizes, all right? Same shape, 2 different sizes. That's basically what similarity describes. So ratios are extremely important, all right? That's if you want to go into certain types of fields, right? So before I move forward with an example of how this is used in maybe a geometry class, I just want you to think about why ratios are important, why they are possibly useful. So just think, this is a person who dreams of a big house, right? Before that house becomes a house, they have to have it or sketch it in their mind first. Whatever they can dream up, they can put on paper, and from that paper, they can expand it to a real house. You get what I'm saying? Literally, it goes from something this small to something real life size, right? And the only way that happens is we got to understand how ratios work. Like when architects draw blueprints, when they draw a blueprint, they don't draw a blueprint that is the actual size of the building. They have to fit their blueprint on a sheet of paper, and then from their mind, they can expand it to something in real life by using proportions and ratios, all right? So that's why ratios are important. All right, so working example, we have a right triangle, side length of 2, the other one of 4. We have another right triangle, side length of 6. This one is an X. So we're going to have to start with some similarity. All right, similarity. So I have BC, then I have CA. BC, CA. BC over CA. So I come over here and repeat that same thing. I got an EF over FD. EF over FD. This right here is going to be how we get to solving that missing variable. All right, so BC is a 2, CA is a 4. That's why I have a 2 over 4. EF is a 6, FD is an X. That's why I have a 6 over X. We go straight into verifying. Just the way we verify when we know all 4 numbers is the same thing, even if one is missing, all right? So if I multiply these 2 together, I get 2X. If I multiply those 2 together, I get 24. Now I have 2X is equivalent to 24. What is X? Yep, so if I have 2 times X is equal to 24, that X value must be 12, all right? So 2 times 12 is 24. That missing value is 12. That's how long that side is based on similarity, all right? Similarity. Okay, so that's where I'm going to stop today. Tomorrow I might do like maybe 2 more examples, the kinds where the triangles aren't turned in the same direction and where you might have to read the statements out properly if you want to get it correctly. So one of the main things is, remember, a ratio is a relationship between 2 quantities, all right? And if you have a relationship between 2 quantities, you can set them equal to each other to verify if they're the same. If they're the same, then that's how you know you're dealing with equivalent ratios, equivalent fractions, similarity. All right, so that's how similarity works. It works off of the same rules that we verify fractions.